Begin. Welcome, everyone, and this is the question I wanted to ask you. Now, just just remember what you would have said. This is the question I want to ask everyone. It's actual question about the plane flying, making a round trip. But if the last time the round trip was up the stream and down the stream, now it's a 90 degrees to the wind. So what I want to do, I want to ask you, everyone, here, there, to draw a picture which clearly shows the plane traveling due north, the vector representing the velocity of the wind relative to the ground, the vector representing the velocity of the plane relative to the ground, and finally, for the last part, the vector representing the velocity of the plane relative to the wind. So here we could have asked two different questions here. If the plane flies due north, what is the direction? Well, flies means of the plane velocity relative to the ground. Well, in that case, we would say north, of course. So the real question is, how should we aim it? And again, it's very similar to the boat crossing the river. So please draw a picture. And then, please, take your smartphone. Take a picture of your picture and email it to me. Well, please don't change your picture. Yeah? So stick to what you've said or sent, and let's just solve it. Keep sending pictures, please. So north, south, east, west. Yeah? Round trip. This is supposed to be the displacement of the plane relative to the ground, which means relative to the person standing on the ground and watching the plane flying. So this arrow is supposed to represent the velocity of the plane relative to the ground on its way due north. The distance traveled, let's say L equals 112,000 meters. Now, the weather report indicates the wind. Okay. This is the velocity of the wind relative to the ground. So, what we can imagine to draw the third arrow, the velocity of the plane relative to the wind. Yeah. So let's say that would have been the velocity of the plane relative to the wind. In that case, the wind would move it away to the right, but the plane should stay on this straight line. So to compensate that motion, the wind, the plane should aim slightly, well, we could call it west of north. Yeah. If that would have been the river, we would have to say slightly upstream. So that's the last arrow we should add, the velocity of the plane relative to wind. And now the magnitude of this velocity, the speed of the wind relative to the ground, is 20. And the last question should be answered is 300. That's what we call the cruise speed. Is it the magnitude of this arrow or of that arrow? We answer this question correctly, done. The rest is just pure, straightforward algebra. If we answer this question incorrectly, well, we will make a mistake. So the cruise speed, that's a term which describes the velocity of the plane relative to, what do you think? No. Relative to the ground if there is no wind, we can say. Which means relative to the wind, relative to air. That's it. So the magnitude of this arrow equals 300. Now, well, we're all set. We just have to apply the law of relative velocities, well, twice, one way and on its way back. And in both situations, we have very similar pictures. This short arrow represents the velocity of the wind relative to the ground. This arrow represents the cruise velocity when it flies from south to north. That arrow represents the velocity of the plane relative to the ground. Now, here, when it comes back from north direction to south, again, we should aim kind of up the stream to compensate the influence of wind. And you can see these triangles are actually identical. So in both situations, the speed of the plane relative to the ground is the same. And if we know the speed and the distance, we can calculate time. And time that way equals time back. So just multiply by 2. Any questions? That's the last actual problem related to relative velocities. So if I've got only one email with a very nice picture, thank you. Keep sending, please. Now, this, oops. Yeah, it happens when you prepare a slide on a Mac and you project from Windows. So that arrow is supposed to be above the last velocity. Both cases are on the screen. The boat crossing the river by the shortest path, the boat crossing the river by the shortest time. In both situations, we have the same velocity of the stream relative to the ground. In both situations, we have an arrow perpendicular to the stream, which represents the velocity of the boat. But, depending on the case, it represents different velocity. When we go by the shortest path, this arrow represents the velocity of the boat relative to the ground by the shortest time. This arrow represents the velocity of the boat relative to river. And we can clearly understand that by drawing the displacement. The shortest path, if you remember, if you've seen the explanation, the shortest path is the path which is at 90 degrees to the stream, to the shores parallel to the stream and to each other. So this is the displacement relative to the ground, which means this arrow, the red arrow, should represent the velocity relative to the ground. Here, because the stream influences the motion, drags it down, this blue arrow now represents the actual displacement. So this arrow should represent now the velocity of the boat relative to the ground. And the time could have been calculated differently. One way, we could calculate the time using the velocity of the speed of the boat relative to the ground. We just have to use the total distance traveled, but exactly the same time we will get if we use only horizontal component of velocity and only horizontal component of displacement. So we could have called it delta x, which is the width of the river, and we should divide it by this of the boat relative to the river, the speed of the boat relative to the river. And that completes all important situations. Now, two balls released from rest and falling down. At first, I don't want to use the balls. I want to use a book which represents the heavy ball and a piece of paper which represents the light ball. So if I release them simultaneously and they will travel the same distance, will they hit the floor or the bench at the same time? What do you think? Well, I'm not collecting your answers, but you should choose your own. Okay? And now we can run an experiment. This is actually very heavy. Ridiculously heavy. So, see? That's physics textbook. I don't know if any person except the author and the editor would have read it completely. So, was your answer supporting the experiment? Well, my experiment actually is not this experiment. The problem with this experiment is, well, there's something else influencing, acting on this piece of paper. They fall down because gravity pulls down, because gravity pulls down everything. But there's also air. We breathe it. And if we try to reduce the influence of air, like this, for example, what do we see? Same time. And of course, we can do the balls. This is a golf ball, it's heavy. This is just a regular ping pong ball. And of course, now the air friction is practically zero, does nothing. So again, simultaneously. Now they travel same distance. It takes same time. We release them from rest, and they move faster and faster and faster. So there's should something they both have in common. If that's motion with changing velocity, we should say the acceleration should be the same for both. I can even take, again, a textbook and a ping pong ball, very light, like 5 kilograms, about 10 pounds, and this is like, I don't know, 1 ounce. Still. So the weight, the mass of this object doesn't matter. All objects, turns out, fall down with the same acceleration. And a similar experiment could have been done if we could have sucked out all the air, from this room. We would die, but physics would work. And this is a very important example of the motion with constant acceleration. And we call it a free fall. Here, close to the surface of the Earth, all objects, when released, travel down with the same acceleration. They could have been traveling up, but with the same acceleration. And on average, that acceleration is equal to 9.8 meters per second squared. If we solve a problem here in the classroom, we usually round it up to 10. But at home, when you're doing web-assigned problems, you have to use the exact value. Now, this is a one-dimensional motion, up or down. We used to use the x-axis for the one-dimensional motion, but now this is a vertical motion. So usually we wouldn't use the same variable x. For the vertical motion, we use a different variable, y. So there's the y coordinate of that object moving up or down. And another thing to remember, an acceleration is a vector. So the acceleration always points down. But it's up to us how we choose the positive y direction. We can choose it up, we can choose it down. If we choose it up, the acceleration points in the opposite direction, so it must have a negative component relative to this axis. But if by any chance you flip it, and you choose your direction down, in that case, the same acceleration will have a positive component equal to 9.8 meters per second squared. So this is just a fact. Another important fact is related to, for example, a cart traveling down a ramp. We did that experiment. With this situation, we also have one-dimensional motion. However, this is a situation when we wouldn't choose axis horizontally or vertically. No, that would actually make calculations harder to do. So if the motion happening along this incline, we choose the axis along this incline. This is, again, a one-dimensional motion with constant acceleration. And what else do we know about motion with constant acceleration? Well, we know the motion equation. We know the graph is supposed to be the parabola, the graph of the position, right? We know the velocity equation, and we know the graph for velocity is supposed to be a straight line. We know that the motion with constant acceleration, the average acceleration, and instantaneous acceleration does the same acceleration. So we just call it acceleration, that's it. And we know that if there's only one motion from t equals 0 to t equals t final, we always can start measuring time from 0. In that case, the velocity equation, the motion equation look very simple. And there is another equation which is not fundamental. These two are fundamental equations. My hope was everybody would actually derive experimentally these equations in the lab tonight. Well, we'll see what's going to happen tomorrow. The third equation is a pure algebraic. You know, if you solve the velocity equation for time and you plug it in the motion equation, so time is gone. And if you do some algebra, this is an equation which sometimes convenient to use if you don't need to know the time, or if you don't know the time, but you know initial velocity, for example, acceleration, and displacement, for example. The same set of equations we can use for the free fall, because as we just said, it is also a one-dimensional motion with constant acceleration. Even better, we know that acceleration, it's 9.8. So these equations become specific equations for any fallen object. We just need to remember again, this minus can be written only if we choose positive y direction upward. So acceleration has a negative component relative to this axis. If we have a complicated motion happening, which is composed of several different motions, in that case, for each individual time interval, we can apply these equations. Yeah. This is, again, this velocity equation, and this is the motion equation. And we can derive the third equation if we want to. We just needed to remember that velocity, acceleration, initial velocity, acceleration, displacement, those are components of actual vectors. And a vector might have a positive component, a vector might have a negative component. So if we write a plus, it doesn't mean this variable is always positive. No, it depends on actual direction of this acceleration. We're going to do some problems real soon. And this summarizes everything related to directions. So we have an axis, and the positive x direction, let's say, points to the right, which is a most common situation. So there's 0. If x coordinate is negative, which it means object is, well, to the left to the origin, to the right to the origin. If x component of velocity is positive, that means velocity points to the right. If it's negative, points to the left. If x component of acceleration is positive, acceleration points to the right, to the left. What does it mean? Well, we know that when velocity and acceleration parallel, and it doesn't matter if they're both positive or both negative, the object is speeding up. If they're anti-parallel, the object is slowing down. Not a new basically not a new slide. Yeah, still we know. In general, the graph for velocity could have been any complicated curve, and the line tangent to this curve represents instantaneous acceleration. But this is the case we're going to talk about. Constant acceleration, again, means just acceleration, instantaneous, average, the same. Velocity equation is linear equation, and actually we have only 3 options. Yeah. Positive acceleration, no acceleration, that's what we used to call motion with constant velocity, negative acceleration. And for each situation, we have some kind of a parabola, the position graph. If you remember math, the shape of the parabola depends on this coefficient. If it's positive, it goes like this. If it's negative, it goes like that. Now let's do an example. So please sketch this picture in your notebook. This is the graph for the velocity as a function of time. And of course, this motion doesn't represent motion with constant acceleration. It's more complicated. And yet we can easily analyze it. Basically, we just need to figure out when the object was speeding up, when the object was slowing down. And the key word is speed. What is speed? Well, we should say full name. The instantaneous speed is equal to what? Anyone? Yes? The magnitude of the velocity. Absolutely. We have to apply this definition, and if we plot the graph for the magnitude of the velocity, that will be the graph for the speed. And what does magnitude do to numbers? If it's a positive number, it doesn't do anything to it. It keeps it. But if it's a negative number, it makes it positive. So the graph for speed will be, well, looking like this. So this part of the graph becomes positive. This part of the graph was positive and remains positive up to here. And now this part of the graph also becomes positive. That's how speed looks like. And now what does speeding up mean? It means speed increases. So here it's speeding up. Here it's speeding up. And here it's speeding up. What does slowing down mean? Speed decreases. So here decreases, here, here. So we can say at this instant, the object is what? Slowing down. But at this instant, for example, here, the object is speeding up. Remember, we said that the area covered by the graph of velocity as a function of time is equal to the displacement. Here we have a similar relationship. Now, the area covered by the graph of acceleration as a function of time will be equal to the change in the velocity. Even if acceleration is not constant, even if it changes, if we calculate the area like that, this area will be equal to, well, this is v initial, this is v final, will be equal to the change in the velocity. Some more examples how graphs could look like. Yeah. Acceleration, positive, velocity is a line with a positive slope, position is a parabola, etc., etc. Now let's do some actual problems related to motion with constant velocity. That's the first one. A very simple problem, but it illustrates the importance of components. So, what is happening here? This symbol v naught, v0, v sub 0 represents the initial velocity. So, the object starts moving from rest, and it reaching speed of 15 meters per second. That's what we call final speed, magnitude of velocity. But if you look at this arrow, the velocity points to the left, opposite to positive x direction. So the x component of velocity, or sometimes we say the actual value of velocity, is negative 15 meters per second. So the magnitude of the acceleration is 5 meters per second squared. Now we can write the velocity equation. The velocity equation says velocity final equals velocity initial plus acceleration times time. Well, we start measuring time from 0. T initial equals 0. That's a normal agreement and normal assumption. We don't even say it usually. Now we plug in numbers. Negative 15 is equal to 0 plus 5 times time. Negative 15 over 5 equals time. Time is equal to negative 3 seconds. Done. Now you should add wrong. Don't do that. What did I do wrong? Well, time cannot be negative. So if we look at the negative time, clearly something went wrong. The question is what? I made a mistake. A certain mistake. Many people make the same mistake. So you have to figure out what kind of a mistake I've made and don't make it anymore. Yes? It is negative 15. Velocity is negative 15 and points to the left.
But if you use I'm sorry, like it's negative x.
No. This is the positive x direction. Everything which parallel to it is positive, has a positive component. Everything which is anti-parallel to this direction must have a negative component. That's what it says. So what did I do wrong? Yes?
The acceleration is also negative?
Of course. The acceleration also must be negative. It says magnitude of the acceleration is equal to 5 meters per second squared, but the arrow clearly points to the left. So the actual value of the acceleration, the actual value of the x component of the acceleration, that's what we should use. So the magnitude is equal to 5 meters per second squared, but the actual value of the x component is supposed to be negative. So that's an easy fix. We just add a minus here, minus and minus makes it plus 3 seconds. So this is an illustration of that fact that every vector has a certain component, and if it's a negative component, we have to use a negative number when we use velocity equation or when we use position equation, motion equation. All right, what's happening here? Well, now we know. Yeah? You see that this blue arrow points to the left. So natural choice for positive x direction is to the right. So the x component of initial velocity is 10 meters per second, but the x component of the acceleration is -2 meters per second squared. These two vertical bars, they represent the magnitude. So the magnitude of this acceleration is 2 meters per second squared. Magnitude is never negative. But the actual acceleration, well, a component of the acceleration is negative. Now, done. The velocity equation. Final velocity is equal to initial velocity plus acceleration times time. And I always advise to indicate the component symbol. So the velocity at any instant will be equal to 10 plus, it's always plus, but we are adding a negative number, -2 times t. And we can plug in any value for t, and that will give us any specific value of velocity. And we can write the motion equation. X is equal to x naught plus v naught x plus ax times squared divided by 2, which is 0 times t times 10 times t. My plus and my t look alike. All right. Plus, well, -2 times t squared over 2. So the motion equation is a quadratic equation. 10 times t minus t squared. -2 over 2 is -1. And, well, when we know the velocity equation, when we know motion equation, we know everything. We can answer any question about the motion of this object. For example, first let's calculate how much time should we wait until this object is brought to a stop instantaneously. You see what's happening? We call it slowing down. Velocity points to the right, acceleration points to the left. So it's moving slower and slower and slower, and eventually it should stop, and then it reverses its direction, and it starts moving to the left faster and faster. That's how we read it. So, when will it stop? If it stops, its instantaneous velocity becomes equal to what number? 0. So, when instantaneous velocity becomes 0, that will be the stopping instant. And we can solve this equation, 10 over 2, 5. So it will stop in 5 seconds. Then it will reverse its direction and will be moving to the left. Now, calculate the average velocity is an easy task. The average velocity is equal to x final minus x initial divided by delta t. That's it. So you need to calculate two values of x. To calculate x final, you have to use t final, which is 12. To calculate x initial, you have to use t initial, which is 1. And then you subtract, and delta t, 12 minus 1 equals 11. The trickier part is calculating average speed. So, what is tricky about that? The distance traveled and the displacement not always same things. So, I just want to clean up a little. What is happening? It starts from 0, and for 5 seconds it travels to the right, and then it stops. Here, we can call it the x of reverse. It changes its direction, and now it travels back. So, when t equals 1, the object was here. That's what we call x1. From x1 to x reverse, that should be the distance traveled number 1. And then from t equals 5 to t equals 12, it travels back. And that will be the new distance traveled. We can call it L2. Any questions on that? If we know what's happening, we know what to do mathematically. So if we're told to calculate the average speed for this time interval, which starts at t equals 1 and which ends at t equals 12, we need to know the total distance traveled between t equals 1 and t equals 12. And to know that distance, we need to see what was happening. So what do we do now? Well, t equals 1. 10 times 1 minus 1, 9. So x1 equals 9. Then, when t equals 5, it stops momentarily, instantaneously. T equals 5, where does it stop? 10 times 5 is 50. 50 minus 5 squared, 25. 25. So for the first part of the motion, it traveled from x equals 9 to x equals 25. So the distance traveled equals 25 minus 9, 16 meters. And now it travels from here to here. How do we find that final position? Again, we can use the motion equation. We know that the final instant is t equals 12. So we can plug in t equals 12. 10 times 12, 120. 12 squared, 144. 120 minus 144, 124. No, just 24. No, negative 24. What did I say? What's the number? 120 minus 144. Negative 24. That's exactly what I said. X final is negative 24. So from x equal 25 to x equals negative 24, distance traveled, L2. Anyone? 49. Yep. Well, 25 up to here and 24 more. 25 plus 24, 49. So now we know everything. We can calculate the total distance traveled divided by 11 seconds. That will give us the average speed. I'm going to skip this problem. I'm going to go talk about this one. That's an example of so-called motion diagram. What we see here is a set of consecutive locations of two objects. Imagine a completely dark room and there is stroboscope light, which flashes every second. So in that case, you don't see anything. Then you see this object here. Then it's dark, and then it flashes again. You see it here, and then here, and then here. So if you look at this motion, can you tell me if it's happening with constant velocity or constant acceleration? The number 2. It travels same distance every same time. So, constant velocity. The top one, again, imagine, it's a stroboscope. So every second you can see. This is how much did it travel during the first second. During the second it travels longer distance. During the third second, it travels even longer distance. So it's speeding up. It moves faster and faster. And the general assumption is this motion happening with constant acceleration. Well, for this guy, it travels 1, 2, 3, 4. We can call 4 units or 4 meters over 1 second. That's the average instantaneous just velocity of the object number 2. For the next guy, it starts from here. It says from rest. So the initial velocity, this is t equals, oops, it's starting happening. All right. So this is the initial position. We can call it number 2, 2 squares. And this is t equals 0. And the initial velocity equals 0. Now, the next position, we can call it in a second. Yeah. So this is x1. T equals 1. X1 equals 1, 2, 3, 4. 4 blocks, 4 meters. Well, we don't know velocity. We will be able to calculate it if we figure out the acceleration. But if we wait 1 more second, so t equals 2. X2 equals 1, 2, 3, 1, 2, 3, 4, 5, 6, 8. 8 blocks, 8 meters, etc., etc., etc. We don't need too many points. If we write the motion equation, and we apply this motion equation twice, using t1 and x1, and using t2 and x2, that's it. We can calculate, well, this is actually 0, so we can, in this situation, when it starts from rest, we don't even need the second equation. We can calculate the acceleration. We just use 4 equals 2 plus 0 times 1 plus acceleration times 1 squared over 2. 4 minus 2 is 2. 2 times 2 is 4. 4, well, units of distance over units of time squared, or we can call meters per second squared. Any questions? Again, we're not learning anything new. We're just applying the same reasoning to different situations when we have a motion with constant acceleration. The free fall. What do we know about it? Everything. In addition to all the previous equations, we even know the acceleration. We just need to remember that everything is happening relative to a certain positive direction. In this situation, positive y direction. And everything is happening relative to a certain choice of the origin, of the 0. And this picture is missing that information. But if you look at the data, we can extract that information. First of all, 0. 0 has been chosen at the initial location of this ball. It doesn't have to be that way. It could have been on the ground, for example. We could have measured it from the ground. And another thing, you see below 0 we have negative numbers. That means positive y direction points upward. Again, doesn't have to be always that case. If we switch it, our numbers, this whole set will be different. So it's mandatory, it's very important to show very clearly positive x direction and the origin. Well, let's solve this problem. You shoot a ball, or you toss it. Yeah. It's a one-dimensional motion. And on its way up, at any instant, at the highest location, on its way down, the acceleration is always the same. We call it a free fall acceleration. It's magnitude 9.8 and it points down. That's a fact. So, on its way up, velocity points up, but acceleration points down. So, how do we call it? Slowing down. It's slowing down. And eventually, it stops momentarily. That's what we call the point of reverse, right? And then it's speeding up. So, this motion is no different from the motion of a cart on a track. Nothing different. So here, that's my hand. Yeah. This dot represents the ball when it doesn't touch my hand anymore. Yeah. So that's when the free fall starts happening. Before that, my hand was moving. That's not a free fall, no. But only when my hand released and it's just flying, and we neglect the air friction, that's what the free fall is about. And the initial velocity points up, and the speed initial equals 12 meters per second. Now we have to choose the direction of the y-axis. It has to be a vertical line, but we can choose it up or down. I say 99% out of 100, choose it up. That makes life easier. Now, we have two important locations of this ball. Number one, the initial location, and number two, when it stops. We can choose the origin either way, but normally the rule of thumb is choose it at the lowest location of your shoot. If I move away, it goes out of the focus. At the lowest location of an object, so here. Here it instantaneously stops. So at the highest point, this is y max, highest point of the trajectory, the velocity becomes equal to 0. It stops momentarily. Highest point. So what does it tell us? Well, we can immediately calculate how much time does it take to reach the highest point. If we apply the velocity equation, velocity final equals the velocity initial plus acceleration times time. Now, for this particular instant and relative to this positive y direction, velocity is 0, initial is 12, acceleration is negative 9.8, but we rounded 10, times time. This time I call time up. It is how much time should we wait until it reaches maximum height. After that, it will be traveling down. It's easy to show that to reach my hand again, if I catch it at exactly the same level, it's going to travel exactly the same amount of time. So time up and time down are equal. Only if the final level where I catch it is the same as initial. Of course, if I toss it and I wait when it hits the table, time up is less than time down, because on its way down it travels longer distance. So time up equals 12 over 10, 1.2 seconds. Now what we can calculate is this maximum height. It's about height, so we have to use the position as a function of time, the motion equation. Y final equals y initial plus v initial times time plus a times time squared divided by 2. That's the motion equation. How can we use it? Well, just plug in everything we know. We start, so we are looking for the maximum height. Just a second. We start from the origin because we made that choice. The velocity, initial velocity, is 12 because we can read. Time up is 1.2 seconds because we have it found. Plus, the acceleration is negative 10 because it points the opposite to y-axis times time up squared divided by 2. Now you take a calculator and you finish your calculation. Done. All right, thank you. Now you can solve so many homework problems. I don't even count how many. I don't know. All right, thank you, everyone. We are done for today. Unless you want to go to the lab. No? It's set up, it's ready. All right, yeah. I'm not sure how much time the camera was out of the focus, so, but you can always send me an email with your questions. And by now I have 10 pictures, which is better than one. Yes?
I'm so a little confused about lab.
No,
No pre-lab or anything.
no.
Are we turning in the lab for during lab, or do we have a week to work on it and everything?
Your lab here will tell you everything.
Okay.
It's very simple. You come in, you do the lab, you leave, you take everything with you. Ideal. If everything goes as planned, and that's it, and you're done.
I have a question.
Yeah.
The first problem we did today.
With the plane,
Yeah.
round trip, okay.
So you have these two, the picture is here, this equation here. But I noticed how you did you do Pythagorean instead?
Yes, I used the Pythagorean theorem.
So,
But if you look at this picture, we know this. This is p100, and that's a hypotenuse.
yeah.
And we know this. This is no. We know this. This is wind. It's 20.
Mm-hmm.
So if we know the hypotenuse and we know this side, we need to calculate this side, and that's what I've done.
Okay. So when I apply this, it ends up, like if I do the numbering, it ends up being 320. So I was wondering when is the time to use that and when is the time to use Pythagorean?
That's the wrong question. The right question is, what's the difference between these symbols and these symbols? The difference is, those are vectors, arrows. This symbol just represents a specific arrow. So you can't plug numbers into this equation, never. So on my slide, I actually had little arrows above it. It represents a vector, a vector, a vector. But if you want to relate the actual magnitude of each vector, in that case, you should look at your specific picture and figure out what to do.
We should never just add the vector to the velocities.
No. No.
So we really shouldn't apply this numerically. We should just always use Pythagorean.
Absolutely. You never should apply that numerically. This is a pre-picture equation. So you write this just to remind yourself that you need to draw a picture which represents it. Then you draw a picture. And then you do the numbers.
I have a question, sir. So when you drop the piece of paper in the telescope, why did the paper fall slower?
Air.
Force of air is actually.
Yes. It's like a sail. I need to decrease the area. I crammed it to decrease the area, and air doesn't matter anymore.
Okay.
So if we had vacuum in this room, even that piece of paper would fall simultaneously with it.
Now, I have another question.
Yes.
So, a negative vector means it's what is a negative vector? Or a
A
negative
negative,
velocity?
well, those are different things. A negative vector is a very bad wording because technically there is no such thing as a negative vector. But people use this term sometimes to describe the fact that vector has a negative component. Like we say negative velocity, we mean that the component of velocity is negative. That's what we mean. Which also means that it points to the left, well, opposite to x direction,
Okay.
which normally points to the right.
Okay.
So this is slang, you know.
Okay.
It's not a very accurate
Not
terminology.
actually negative. Just
Yes,
pointing
no.
in the.
Yes, this is slang, and negative velocity, this slang means velocity which has a negative component.
Okay, I see.